Okay, welcome back. This is still section 3, 4B. We're now on page 2, and we'll go through a few problems here and take another break. The position of a body at time t is, S, this could be S of t, is this cubic in meters. So once again, we're really going to focus in on this. This is the position, because pretty soon, like I said, they're going to give us a velocity equation. Find the body's acceleration each time the velocity is 0. So I need to get my velocity equation, set it equal to 0, find those times when it's equal to 0, and then put those times into my acceleration equation. So easy enough, I think. Velocity at time t is our first derivative of position, so that is 3t squared minus 12t plus 9, power rule polynomial. Shouldn't get much easier than that. I'm going to go ahead and get our acceleration out here. Acceleration at time t is the derivative of velocity, 6t minus 12. So we want to know when the velocity is 0. I don't want to put 0 in here. I want to know when the velocity is 0. Velocity equals 0. Let's go for that. So when is 3t squared minus 12t plus 9 equal to 0? Well, I can divide both sides by 3 in this case and get t, this is t squared, velocity. Oh, yeah, this is our t squared. I'm just bringing that formula down. So I get t squared minus 4t plus 3 equals 0. And that is nice and factorable. That's t minus 3 times t minus 1 equals 0. So the velocity is 0 when t equals 1 or 3 seconds. I don't know why I put the semicolon in there. 1 or 3 seconds. So now I just want acceleration at time 1 and 3. So acceleration at time 1 is 6 times 1 minus 12, or negative 6. What's my units? What unit am I going to use for acceleration? Well, we're dealing in seconds and meters, so that is meters per second squared. And what's my acceleration at time 3? That is 6 times 3 minus 12, or 18 minus 12, 6 meters per second squared. Again, that will be a big issue for us. We've got to label these things correctly. Okay, it takes 12 hours to drain a storage tank by opening the valve at the bottom. The depth, we'll have to interpret that. Y of the fluid in the tank, t hours after the valve opens, is given by the depth y of fluid is given by, let's say that is the depth in, oh, it's in meters. Here we go. After the valve is open is given by this formula. Now I have taken it upon myself here to go ahead and get a graph of that. And of course, tough to see right there. Now, you notice this is going to be a parabola. And first off, maybe it's an upside down parabola. Nope, because when we square this, if I FOIL this out, I get positive t squared. It's a right side up parabola. But because it says it takes 12 hours to drain, I'm assuming we're starting at 0 and running to 12. So how I graphed this was I went window a little bit to the left of 0, negative 1, a little bit to the right of 13, 12. And then I hit zoom fit to come up with this graph. And we can do this without the graph, but I think as we're learning to interpret these kind of problems for the first time, the graph might be helpful to us. So I'm just going to sketch that. At time 0, this thing is just going to be up at 6. And at time 12, it's pretty easy to see. When I put 12 in, divide 12, we get 0, which is what we should, because it says 12 hours to drain. So at 12, but this looks like the left side of a parabola, so it has a curve coming down to it. So we're looking something along the lines of this. So I'll have that there just for interpretation. Don't need that for this, though. This just says find the first derivative at which the water level is changing at time t. So we need, so that's our rate, so that could be like our velocity. I just call it velocity. We could go R of or V of t equals the derivative of our position function. Well, our position function, we could FOIL this out, distribute a 6, and treat it like a polynomial. We can also chain rule this. So this 6 is a constant, 6 times the derivative. This says an inside function, 1 minus t on 12, and an outside function squared. The outside derivative is 2 times something to the first, 2 times the inside function. Then treat the baby, the inside derivative is negative 1/12. So that's kind of convenient here. I notice I get a 12 and a negative 1/12, so that is negative. If I multiply these first, 1 minus t on 12, or we get positive t on 12 minus 1. There's our velocity at time t, and that would be meters per hour. Okay, so find the rate at which the water level is changing at time t. When is the fluid level in the tank falling the fastest? Well, again, I had this graph which I translated here. When it's falling the fastest is when its velocity is the greatest going down. Well, if we're convinced that this is a parabola going down, its greatest velocity going down is when the tangent line slope is the greatest. And that is clearly, we're in a constant state of cupping up here. This is the steepest part at 0. When is in real world context it makes sense, but we still need to solve this through the physics, through the math. It kind of makes sense that the more water's in it, the more pressure is going to be for it to drain out. So it does kind of make sense that the speed at which it's draining out slows down. When is the fluid level in the tank falling the fastest, the slowest? Our fastest is at t equals 0 seconds. And that rate would be velocity at time 0 is, our velocity function at time 0 is negative 1 meters per hour. And then, whoops, I'm sorry, I didn't have that showing. Fastest is at t equals 0 seconds. And our slowest is at, and that you could even deal in speed. The speed is at a rate of 1 meter per second. So draining at 1 meter per second. And it's the slowest at t equals, what do we decide on that? T equals 12 when we're done here. It's getting less steep, less steep, less steep. So when we put 12 into this guy, it is now draining. We get velocity at time 12 is 12 on 12, 1 minus 1, or 0 meters per hour. So it is draining at, I guess I didn't need to do that. This should be hours, meters per hour. So sorry, I'm kind of piecemealing this together. I've got some students coming in, talking, and looking for questions. So I'm trying to serve everybody I can here. Draining. That's terrible, embarrassing. I'll get over it. Okay, hope that's helpful, and you can stay tuned for the third page.